So in this video we're going to take a look at some past exam style questions on radiation and radioactivity. So we've got strontium-90. It's a radioactive isotope that emits beta particles as it decays. The nuclear equation shows this decay. Calculate the value of A. Well, it must be equal to 90 so that the nucleon numbers match up on either side of the equation. And the value of B must be 39. So again, the proton number adds up to the same number on both sides of the equation. Nucleon number and proton number must overall stay the same in any nuclear decay. Okay, so tick the element from the list that is produced. So we had this yttrium, that's the one with the proton number 39. An isotope ABX is also radioactive and undergoes beta minus decay. State the name of the element that is produced by this decay. While in the process of beta minus, a neutron turns into a proton, so we're going to increase the proton number by 1 again to 40, so that's going to be zirconium. 3 nuclei are represented, so we've got X, Y, and Z. State and explain which nuclei are isotopes of the same element. So we're looking for ones which have the same proton number, which is clearly X and Z. They both have proton number 42. So there are 2 stable naturally occurring isotopes of hydrogen. We've got the common one, hydrogen 1, which is proton number 1, nucleon number 1, which means it has no neutrons. Hydrogen 2 has 1 proton and 1 neutron, and then there's tritium, which has 1 proton and 2 neutrons, and that's why it has a nucleon number of 3. So complete the table. So the number of protons is easy. They're isotopes of hydrogen, so they will have number 1. Number of neutrons, we've just discussed. Essentially, these 2 numbers added together should give you the nucleon number. So that's how we get 1, 2, and 3 respectively. And the number of electrons will always be equal to the number of protons unless you've used something to ionize the atom. Okay, so 2 samples of tritium are stored in aluminium containers of different thickness. Sample 1 is a container of thickness of 0.5 millimeter and you can detect radiation. Sample 2 is thickness 5 millimeters and no radiation comes through. State the type of radiation. It's going to be beta. And the reason we know that is essentially I do this by elimination. So alpha would be stopped by both of the containers. 0.5 millimeter would be more than enough to stop alpha, and neither of them would have stopped gamma, so we'd have got radiation for both of them. So by process of elimination it must be beta, and it also matches up with what we know. We commonly see that beta can be stopped by 5 millimeters of aluminium. That's like a common fact. Under conditions of extreme high temperatures and pressure in the interior of the sun, hydrogen nuclei can join together. Name this process. Well, it's called fusion. State whether energy is released, absorbed, or neither released nor absorbed during this reaction. It's released, and that's why the sun is emitting energy into its surroundings, which we are the beneficiaries of here on Earth. So when a nucleus of a certain isotope is bombarded by a suitable neutron, it splits into 2 smaller nuclei and energy is released. That is called the process of fission, and this is the process occurring inside nuclear power plants. You destabilize an isotope with a neutron, and then that causes fission, which releases energy. So in a laboratory at a nuclear power station, a radiation detector is connected to a computer. The readings are displayed on a screen. The detector is switched on. 10 minutes later, a small sample of radioactive material is removed from a nuclear reactor and placed near to the detector, and the readings are recorded for a further 40 minutes. Okay. So, use the diagram to determine the background count rate. So let's have a look at this diagram. So you can see background would be the reading before the detector, if the radiation is put near the detector. So this is going to be background, so we can see that it is 12 counts per minute. So it wants us to use the diagram to determine the count rate due to the sample at 10 minutes and 19. So the total count rate at 10 minutes, I reckon, is 84. At 90 minutes, I reckon, is 21. But to get the count rate from the sample, we have to subtract our background count rate to give us the counts just from the sample. Using the values, estimate the half-life of the radioactive sample. Well, 72 divided by 9 gives you 8, so its activity is halved 3 times. 2 to the power of 3 gives you 8. So 3 half-lives is 9 minutes, 1 half-life must be 3 minutes. And to get half-life, you must have subtracted background count rate in your calculations. Okay, so in a laboratory experiment, the isotope uranium-238 is used as a source of alpha particles. State one feature of uranium-238 that is the same for the nuclei of other uranium isotopes. That's the proton number. So the other common isotopes being 235, which is the one you want for nuclear weapons and nuclear reactors, but you also have 236 as well, quite a common one. One feature of uranium-238 nuclei is that it's different for the nuclei of other isotopes. It's the neutron number that's different. So the diagram shows alpha particles from the uranium source being directed at a very thin gold foil in a vacuum. Okay, and we've got a detector to see where they go. To investigate the scattering of alpha particles, the detector is moved to different positions around the very thin gold foil and the measurements are recorded. Describe the results from this scattering experiment and explain what they show about the structure of atoms. Okay, so most alpha particles go undeflected, indicating that most of an atom is empty space. Okay, that's the first general finding. But then you find that some alpha particles are deflected by large angles, so they almost bounce backwards. So it indicates that there's a very small, highly charged nucleus that contains most of the mass. And this underlined section is something you look for in an answer to this question. That's where most of the mass is. This experiment actually doesn't tell you necessarily what the charge of the nucleus is, but it tells you most of the mass must be there. Complete the following statements. An alpha particle consists of 2 protons and 2 neutrons. A beta particle consists of a fast-moving electron. So it's not just an electron, it's a fast-moving electron. As alpha particles and beta particles pass through a gas, molecules of the gas become ionized. Explain what is meant by the ionization of a gas molecule. So, when the gas molecule has an electron removed, technically, ionization can also be the addition of an electron, but in terms of radiation, we're talking about the removal of electrons. Okay, so the diagram shows a beam of alpha particles and a beam of beta particles in a vacuum. The beams are about to enter a region in which a very strong magnetic field is acting. The direction of the magnetic field is into the page. Suggest why the paths of the particles are curved. Well, they're going to be curved because the charged particles are travelling perpendicular to the magnetic field, so there'll be a magnetic force between them. Sketch the paths of them. So if we use Fleming's left-hand rule, the field is into the page, so that's where our first finger points. For the alpha particles, they're positively charged, so our middle finger points from left to right. So you can see the alpha particles will bend upwards. Beta particles have the opposite charge, so they bend in the opposite direction, and because they are so much lighter than alpha particles, the force is going to cause them to be in a much more curved path, because even though they're half the charge, they're something like 2,000 times smaller, so that's why we get a much bigger acceleration for beta particles than we do for alpha particles. And that completes this video looking at some particle physics.